right, let us begin. Take record here. We have Claudia's here, and I won't call her Krista ever again. Sarah, Isabel, David, Andy, Jenna, Anna, Max is here, Aaliyah, and Diana, all here. Okay, review. First, while I'm reviewing, go to Woo Clap, because we're going to do Woo Clap for like a whole bunch of things. On Monday and on Tuesday, we talked about electric potential for multiple charges. Then we talked about some biological things, mostly in the heart. And then in lab, we talked about resistance and Ohm's Law. Today, we're going to jump back to do capacitance. And then we're going to talk about Kirchhoff's laws and how we analyze circuits. And first, I want to ask you some review questions, hence the Woo Clap. So, 3 people got connected before I showed that.
I need like a full 5 minutes to let my laptop.
I'm actually believing you.
Yeah. Sorry.
You must be the one who's never participating.
Actually, I can do it on my phone. Because my phone's on 12%. Oh, okay.
It's the morning.
It's a good reason.
It's reasonable, yes. Okay, we have 7 connected here. 8. 2 more. 9. Yeah. Looking for full participation. I can't even tell who's connected, so I can't say, Max, you're not connected.
I'm very much connected.
Max is connected, though.
Even here's the thing, the school Wi-Fi is also very slow.
That's true. How do I know this? Because I was trying to load the homework site the entire 5 minutes before class. Okay, well, let's go ahead and get started. So, what part of the EKG is produced by the recovery or repolarization of the ventricles?
The repolarization.
The repolarization, yes.
What's the name of the 3 things again?
The what?
It's like Q something something.
Well, these are all your options here. I will answer after you guys do. I just want you to think through what you know.
It's P, then it's like the normal thing, then it's T, which is the repolarization. Yes, and they're fine.
So then what is the last one?
P is first that one is first kind of. No, like this first little pump thing. P.
Okay, let's get at least 2 more people in here. Ideally, we get 3 more people. Okay, all 9 of the people who have logged in have answered. So here's what we have. We have 0 that said J, which is good because J is not one we talked about.
This is good.
And we have 0 that said P. We had 1 that said a Q, 1 that said an R, 0 that said an S, 7 that said a T, 0 that said a U. Now, I believe the J and U waves are legit waves. I looked stuff up when I made this question, but I don't know what those are. What we learned was this one here. Okay, I have to change color so we can actually see a contrast there. That there was the P wave, and the P wave was the depolarization of the atria. That's the atria pumping blood into the ventricles. This here, I heard people saying it, is the QRS complex. We don't generally break that up. That is both the recovery of the atria and the recovery being repolarization of the atria, and the depolarization, the pumping of the ventricles. And then that leaves for us our correct answer. The T wave is the recovery or repolarization of the ventricles. Yeah, those are the main ones we look at. Looking at other things is only for people who actually are like cardiologists or, into that kind of thing. The T wave is really important to me because if you have an inverted T wave on lead 3, that means you're not getting enough oxygen to your heart. And that's the situation I found myself in. Okay, next question. What is Ohm's Law? One of these equations is Ohm's Law. Every single one of these equations is a correct equation. The only one is Ohm's Law. Yeah. I'm not exactly sure how you redo it, but yeah. Hey, we got all 10 people connected now. Okay, 9 people have answered. Max and everyone who's correct. Well, no. I'm saying that because Max said that he actually entered the wrong one. So I'm giving him the credit for knowing what the correct answer is. So we have 9 people who've answered, but 10 are connected. I'm just going to go from here. Well, oh, there we got the 10th person in.
I knew it. I'm an idiot. No, I messed up.
I gave you credit there, though. I said you knew you messed up, Max. So this is Ohm's Law. Now let's focus on the meaning of this, right? This is what we were working on verifying in lab yesterday, that this was correct. What is V in Ohm's Law? Not just voltage. I want something more specific. It's the voltage drop across a resistor. So you have the resistor, and you have, let's say current is going like that. Which side has a higher voltage? Okay, the left side. How do you know the left side? Okay, because the current, even though in reality it's electrons going the opposite direction of this arrow, we talk about a mythical positive charge, and that positive charge is losing energy as it goes through the resistor because it takes energy to force it through. That's what resistance means. So it has a higher energy per charge going in, a lower energy per charge going out, and this V is that voltage difference, the voltage drop as the current goes through. What is I? Not just current, but the current going through. Right? The voltage is across, the current is through. That's the thing I'm trying to emphasize. That's why when you measure the current, you have to break the circuit, put your meter in there to measure how much is going through. But when you measure voltage, you just connect in parallel because you're just looking for the difference across it. Right? So there's important things there. And then, of course, what is R? It's the resistance at the end. Now let's look at these other equations. Some we've seen, some we haven't. The top one, power is current times voltage. That's the power either consumed, absorbed is what we say, or supplied. Remember, the units of I is coulombs per second. The units of V is joules per coulomb. So if we multiply these by each other, what do we get? Joules per coulomb times coulombs per second. Those coulombs are going to cancel, and that's joules per second. And that's power. Now, a resistor always absorbs power. A resistor is never supplying you power. So if you have the current and the plus and minus the way it is for resistor, that's the configuration that gives you absorbed power. If it goes the other way, that would be supplied power. So for a what did I just draw? I drew a cell. Which side is positive? Okay, these are actually questions coming up, so I'm reviewing for the next questions. What direction should current be flowing? It should go out of positive and into negative. Right, so it comes out of the positive, goes into the negative. What you said was fine. I just wanted to make sure. If you say from negative to positive and you think through the circuit, you're wrong. But yes, like that. So in this case, notice I had plus and minus reverse from what it was on a resistor. And that tells me, oh, it's supplying power. You can charge a battery. You charge a battery by forcing the current to go the other direction through the battery. That forces the chemical reactions to run in reverse if you have a battery that the chemical reactions can be forced to run in reverse. If you don't have a type, right, the car battery, the lead acid battery, you can force the chemical reaction in reverse if you put extra electrons on the one that's supposed to be negative. But in like a typical battery that you have here, it'll just blow up. So you don't want to try to charge non-rechargeable batteries saying, oh, I'm going to save some money. They didn't put non-rechargeable, but they're all chemical reactions. Yeah, some are not reversible. Okay, so power is either the power absorbed or the power supplied. It depends on the direction of the voltage versus current. And remember, the resistor one is always this way, and that's always the absorbed example. Okay, the next one, voltage difference is electric field multiplied by distance. Aaliyah just checked a problem with me, and that was the solution for a problem. It's also the first slide we're going to have, I think, after I get through these questions, is reviewing that topic. Because it's only correct in a certain situation. It's not generally true. Voltage difference is change of potential energy over charge. That's the definition of electric potential, right? And then finally, resistance is resistivity times length divided by area. Bigger wires have lower resistance. Longer wires have higher resistance. Resistivity depends on the material. Okay, next question. Of course, I did just review these. Oh, I wanted to make this so it was in that way. Woo! Did that change the display on your phone? How do you identify the positive side of a cell in a circuit diagram? We are 80% done. 2 to go. We are. Does it tell you that? No. Okay, 9 out of 10. One more to go. There we go. All 10. Ah.
100%.
No.
No,
The last. How do you can see that?
No.
Okay.
no.
Yeah. The last person.
Yeah.
The last person said the short side is positive. It's the long side that's positive. So looking at this side's positive. Just like in this backward. Come on, go backward. In this picture I drew here, we had the positive with the long side. It's always the positive is the long side. All right, next question. Yeah?
Can you also just say the plus side tells you it's positive?
It's generally not there.
But if it's there, then it would.
If it's there, then it would, yes. Okay, which terminal of a power supply or cell or battery does current flow into?
Now, are you talking through the circuit or from one node of cell to the other node of cell?
I'm asking, does this here would be A,
Okay.
this here would be B.
Wait.
It depends on if the if the power supply is absorbing or supplying power.
You got me.
We'll be good. We'll be good, Max.
You got me.
No,
No, you
no, I don't got you.
got me. What does it depend on? It depends on if the
Power supply is absorbing and not be submitted.
Okay, I started again. Okay, so we got 9 answers. I'm just going to assume that the other person tried to answer when I had it timed out. The answers we have are 1, 7, 1. So there's a pretty good agreement there that current should flow into the negative and out of the positive, and that is correct.
Did you just say like something about power supply or something like that? You can like reverse it.
Okay, so that's right. You could charge a battery. The reason I used a power supply is if you have a power supply with the current going bad, you're probably going to make it break. And so you don't want this to happen ever with the power supply. I originally had it with the cell, but with the cell, you couldn't be charging it. So that answer depends on if it's supplying or absorbing power. That would be true, but power supply should never be absorbing power. A cell could be because you could be charging it. So that answer, I mean, if you were thinking it through and you had that in your head, then you still had a good understanding, right? The goal here is to check our understanding, not to guess which one I wanted you to answer. Next question, a matching question. Match each term. Good, it stayed in the same order. Match each term with what it is measuring.
Is it possible to access like these quizzes and stuff outside of class?
No, but they are in the slides that you notice I'm not using the OneNote because we had a lot of issues with it last semester. I'm just putting everything on Moodle. So you can look at the slides on Moodle, or of course you can also look at the YouTube video. It'd be in either place.
Oh, okay. And then, so the answers would be there too?
Oh, sorry, I'm restarting it. Well, what I circle here, right, I on the slides, I put the number of responses and circle the answer, so it would have them on the slides, yeah.
Okay, thank you.
Yeah. Okay, we have 7 out of 11. Okay, anyone else still answering? Well, let's see what we have. For current, the most popular answer for current, with 5 people answering it, was the rate of flow of charge, and that is correct. Current is the rate at which charge is flowing. For voltage, the most common answer, with only 4 people answering this, was the potential energy per unit charge, which is correct. Resistance. 4 people answered energy required to force charge through. They were also correct. Power. Power, a topic from last semester, came in with the lowest correct answers. 3 people said power was the energy required to force charge through. That's not it. That was resistance. 2 people said the rate at which energy is converted. That is rate at which energy is converted, B. That is the correct answer.
Hey, I know 2 things.
You know many more than 2 things. So these are important topics in circuits. Power, the rate at which energy is converted. If it's power absorbed, then it's energy that's being converted into heat probably. If it's power supplied, it's energy given to electrons in reality. All right, we're getting to the end here. How do you connect it's the next last question. How do you connect a voltmeter to measure the voltage drop across a resistor? Okay, we have 8 answers.
Our stupid thingamajig was broken.
Stupid thing was broken.
The stupid phone, it's not stupid.
Oh, yeah.
It was not working.
Unfortunately, that one got put back with the rest. I was going to check it out. Well, guess we won't check it out today, will we? So we had 0, 8, and 2 for our answers. Series will not work. If you put the voltmeter here, you have no knowledge about what the difference was across the resistor. Voltage is measured across the resistor. So voltage has to be measured in parallel. And now for our final question. How do you connect an ammeter to measure the current through a resistor? Okay, we've all answered. So it's through. When you're measuring the current through, it has to be in series so that any current that went through the resistor had to go through the ammeter. So once again, parallel will not work. That won't tell you about how much went through the resistor. It'll only tell you about a difference from one side to the other. So these last two are really important. For lab next week, you're going to be measuring current and voltage again. And you have to know how to measure it. And somewhere in your life, hopefully, you'll find yourself in a situation where you need to use your little multimeter to measure something, and you need to know how. I say hopefully. I find myself probably once a year. It's not very often. But it's important to know how to use it when you have to do it. And given that you're in physics class, you're going to be the one who knows how to do these things in your household. Okay, I said the next slide. This is leading into it. Equipotential lines are lines where you have constant voltage. That is, if a charge moves along those equipotential lines, there's no energy gain or loss. And so you've already seen, I drew at the beginning of class on Monday, the picture on the left with the equipotential lines. And then we've got some samples of what the equipotential lines would look like if we had two negative charges. The electric field lines, we talked about those a lot previously. Now we're talking about the equipotential lines. Now, what we want to deal with, what this is bring us to, is how we can calculate the change in voltage if you move in a distance that's not on an equipotential line. If you stay on an equipotential line, there's no change. And we start with and for this class we end with, the simple case of a uniform electric field. How do I know it's uniform? Well, the lines are all parallel to each other, which means the spacing between them is constant, which means the electric field strength is constant. So the direction is constant and the strength is constant. That's uniform. If you move from here to here, then you're going to have the work done by the electric field is the force. Well, force is the electric field multiplied by charge. So the work is force times distance, but force is QE times the distance I moved. And since potential energy, I used U here for potential energy, I probably should have used PE. You're more comfortable with that, right? So the change in potential energy is defined as minus the work. And so that's minus QED. And then the change in voltage is minus the change in potential energy, so minus the QED or minus ED. So the change in voltage is minus ED. What does the minus sign mean? That means that if you're going with the electric field, you're going to have the voltage drop.
Are we done with blue clap?
Done with what? The blue clap?
Yeah.
There's one more at the end of the lecture if we get there.
Okay.
We're done with the big string of questions. So this relationship, when does this relationship hold true? It only holds true if you have a uniform electric field, number one, and number two, if D is parallel to that electric field, which those two cases have to be true for this equation to be true. And that's the only place where you would be asked to find a relationship between voltage, electric field, and distance, because otherwise it's going to require something like calculus. So David, you can ignore me when I say that's the only place. Because you can do calculus. So the homework problem that Aaliyah was asking me about, let's just look at that problem real quick. That was the wrong thing. I accidentally hit the thing to stop the presentation instead of the one for the whiteboard. That's the right one. So the problem that Aaliyah was asking me about, you have a uniform electric field like this, and then you have a point A, and you have a point, well, I'll put B in the same color, a point B, and point B is north of point A, and the electric field is pointing south. This distance here is given, and the strength of the electric field is given. I'm going to use what numbers I remember. I believe it was 100 volts per meter. What was the first units we learned for electric field? It was based on force. Remember, electric field was defined as the force per charge. I'm too high and I can't put a vector sign over that F. Force per charge. So that would have units of newtons per coulomb. This has volts per meter. A volt per meter, a volt is a joule per coulomb. And of course, divided by meters. But a joule is a newton meter. That's supposed to be an M down there. And those meters cancel. And so a joule, or volt per meter is equal to a newton per coulomb. So this is still a valid unit for electric field. So you can just change from newtons per meter to joules per coulomb. It's the same thing. Based on the equation we just saw, change in voltage is equal to minus electric field times distance parallel, which would be minus 100 volts per meter. The distance parallel, this was anti-parallel because it moved that way. So it'd be minus, and the distance was 2 meters for Aaliyah's case at least. And so minus a minus is a plus. Delta V is equal to 200 volts. So going from A to B, the voltage would have to rise 200 volts. So that's a very straightforward application of our equation that delta V is minus dV. I'm sure there's more to that problem, but that was the part that Aaliyah asked me about. That's the part I remember to do. Anyone have a question about how that worked out? Okay. Question for me?
No, I make sense now. I was just like,
Okay, back to presentation. Capacitors. Capacitors, not capacitors. I had a friend always call them capacitors all through physics class when we were in college. Capacitors are devices that store energy in the form of a charge separation. So if you look at the picture up there, we have a physical battery, and it's connected to two metal plates, two conducting plates. And those plates are in a reasonably close proximity to each other. And so when you connect it to the battery, one pole or one terminal of the battery is negative. So this side here takes on a negative charge. One terminal is positive, the other one takes on a positive charge. A battery does not store charge. It doesn't create charge. It just gives energy to charge. And so if you start out with these two metal plates both having zero charge, that's the same number of electrons as protons in the metal, and you connect it to the battery will fundamentally pull electrons off of one side, making it positive, and deposit that same number of electrons on the other side. So one side is marked as plus Q, one is minus Q. We generally just say this has a charge Q. One side is plus Q, one side is minus Q, and we call each one of those is just Q. That's the charge on the capacitor. It's important that you realize the nomenclature. You could think 2Q because one's minus Q, one's plus Q. The difference between the two is 2Q. But Q is how much charge was moved from one plate to the other plate. Now, what's going to happen when you have a positive charge on one plate and a negative charge on the other plate? It's going to create something we've been talking about a lot. Create a what? I'm sure you all know the answer, but it's hard to think about what is he trying to psychically tell me. It's going to create an electric field. What direction should these field lines point? Out of positive into negative. So it's going to create an electric field like that. And so I said it stores energy in the form of a charge separation, because we have plus Q on one side and minus Q on the other. We can also say that it stores energy in the form of an electric field, because it creates an electric field between those two plates. So that's the fundamental, that's the only capacitor design we talk about in general physics class. Now, if you're designing a capacitor for commercial purpose, you're going to be much more complicated in your design. We call our design a parallel plate capacitor. So these pictures on the left are showing you capacitors that you might buy for different purposes. This here is a capacitor, it's a ceramic capacitor. This here is a rolled capacitor. Here's a picture of a rolled capacitor. You have one plate, and then you put an insulator, another plate, an insulator, and you roll it up. I used to do a lab where we did this. We would take cellophane, that was our insulator, and aluminum foil, that was our conductor. So you put cellophane, aluminum foil, and you roll it up, and you make a capacitor. And then we actually measured the capacitance of it. So what's the purpose of the capacitor? Store energy. It stores energy, and then you can say either in the form of a charge separation or in the form of an electric field. Either is an accurate description. Now, how do they work? This is a definition. We measure capacitors, I don't even remember where the word capacitor comes from, with a capacitance which is defined as the charge separation divided by the voltage difference between the two plates. And so, I mean, the way I always remember this is by, I remember it that way because there's like a store QVC or something, or maybe it's a shopping channel. There's something that's QVC. That's the way I remember it. But that's the definition of capacitance. It's simply relating how much charge you separate with the voltage difference you put on the plates.
Is like this E equals Q over A? Is that epsilon like a number?
Epsilon is, I will get to it, but it's the permittivity. It's not permittivity of free space because it doesn't have the subscript of 0. It's the permittivity. But I will talk about that in very brief. Now, going from this definition of capacitance, if I have a parallel plate capacitor, so this equation here is only valid in the case of our parallel, a uniform electric field, and D is parallel to E, which means in the parallel plate capacitor form. If we have some other more complicated design, this isn't going to be correct. But the voltage difference, I dropped the minus sign because I just cared about the magnitude. The voltage difference is the electric field multiplied by the distance. Delta V is minus ED was with the sign. And so I can put that in for my change in voltage there. And I will have capacitance is equal to Q over electric field times the separation. But then we also know, and this here, somebody in this classroom is doing this for the last problem on his calculus-based homework assignment that was due yesterday.
Yes.
Yes. This is the result of a derivation that is not so difficult, really. Using Gauss's law, that if we have parallel plate capacitors, the electric field between them is the total charge on a plate divided by the area of the plate and the permittivity. And so if I plug that in, Q over A epsilon D. But then my Q's are going to cancel, and that's A epsilon over, Somehow it feels like I made a mistake here, but that's what I have. We'll see what I have on the next page. I think it's right. Now, Anna's question, what is this epsilon? This epsilon is the permittivity of space. That is, how easy is it to pass charge through space? Epsilon sub 0, that's the permittivity of free space. That's how easy it is to pass charge through a vacuum. If you have something that's not a vacuum, then you drop the subscript of 0. And so air is not a vacuum. And so if you have air between the plates, you're going to have the epsilon for air rather than vacuum. Very close to the same. Question, Max?
On the first equation, the
Yes.
3 equals 1. That means the definition, right?
The 3 equal sign means definition, yes. So the key to this is capacitance is based on the physical construction. If you have a parallel plate capacitor, the area of the plates, this is assuming the two plates have the same area, the permittivity of the space between the plates and the separation of the plates are the only things that determine the capacitance. But you don't have to have air between the plates. You can put what we call a dielectric. A dielectric is something that didn't do what I wanted. Zoom in, please. Please. Does it have zoom as an option? Okay. Why can I not zoom today? I don't know. You know what happens randomly when I don't want it to. But if you look here, these show little molecules that have a plus sign and a minus side. We call those dipoles. Let's go back to something I did not emphasize when we first talked about charge. We learned that opposites, do they attract or repel? They attract. Opposites attract. So let's say I have something with dipole moment, something like a water molecule. You guys have all taken general chemistry. I think in general chemistry you learn about the water molecule. A water molecule has an O, an H, another H. Because of the paired electrons, you have a fixed angle of what is about 109 degrees here between the two H's. H, hydrogen, has a fairly low electronegativity. That means the hydrogen doesn't really hold on to its electrons very strongly. Oxygen has a much higher electronegativity. It really wants to hold on to its electrons. It would like to have more. After all, oxygen is 2 columns away from the noble gases, which would have a complete outer shell and be the most stable. So the oxygen wants electrons. The hydrogen, you can take it or leave it. And so what happens is you have about plus 0.35 charge on average for each of those hydrogen atoms. That is, the electron spends about 65% of its time with the hydrogen and 35% of its time with the oxygen. And so it has what appears to be a little positive charge. The oxygen has a minus 0.70 charge because it has the 2 electrons that it's getting more time with. So this is an electric dipole. Has electric dipole moment, and so we could show it as one of those little oblong things with the minus sign being where the oxygen is and the plus sign being midway between the hydrogens. But if I had, let's say, a positive sphere and I have a water droplet close to it, what are the water molecules in that droplet going to do in response to being close to that positive sphere? The water droplets have a negative and a positive side on each molecule. If this is positive and I have this has a positive side, negative side, what's going to happen with the positive side of my water molecules? It's going to be repelled. What about the negative side? It's going to be attracted. So it's going to rotate like this. So the minus of my water molecule is closer to the sphere, the plus is farther. But the electric force is an inverse square law. Things that are closer have a stronger force. And so the negative, the attractive one is the closer one. The repulsive one is the farther one, so it has a net attractive force. And so it's going to be pulled in until it touches. What would happen when the water molecule touches my positive thing? Then we have conduction, and we're going to have electrons jump off of the water onto my positive sphere. Then the water is going to become positive, and then the positive sphere is going to repel the water droplet away. So if you have dry air, static electricity is a real problem, right? You walk around, you get shocked by everything. But if you have humid air, you don't get shocked by everything because the water molecules in the air are naturally going to things that are charged because of that dipole attraction. And then when they touch, they take charge away or repelled, and you drain the charge off of everything. Another cool thing you can do is you can have that Van de Graaff generator. If you run a stream of water next to it, it will curve in. And you don't want it so close that it hits it. But it will curve in because of the water molecules aligning and then being attracted. Now, that's a dielectric. You can put a dielectric between the plates of your capacitor. What is that going to do? It's going to act to make the electric field between the capacitor plate smaller. But if you make the electric field smaller, that means you'll be able to put more charge on there for the same voltage difference. Because remember, the voltage difference depends on the electric field and the separation. So the dielectric makes it so you're going to be able to put, the dielectric weakens the electric field, which means that you'll have a bigger voltage for the same charge. Hence, it changes your capacitance, making you have a bigger capacitance. Did I say that right? Bigger voltage? No, smaller voltage for the same charge. So a bigger capacitance. So your capacitance, if you put a dielectric, we can write the equation like this. Kappa is the dielectric strength. And so kappa times the permittivity of free space gives me the permittivity. So kappa, if you know kappa, you know epsilon. If you know epsilon, you know kappa. It's easier to write it this way. And then kappa is 1 for a vacuum, bigger than 1 for anything else. So what's the point of this dielectric? It allows you to make a capacitor larger for the same physical dimensions. It also might make it so you can put a higher voltage on the plates before you have an arc go between the plates. So it gives us 2 advantages. One is you have a higher voltage, so before it arcs. The other one is you have a higher capacitance. This lower picture is showing the net effect of the dielectric. The net effect is negative on the positive side, positive negative side. Note that the electric field that would be caused by this yellow region would be going in this direction, which is why it shows it erasing those lines. So backing up a step, physical dimensions define the capacitance value. And it's just dependent on the area of the plates and the separation of the plates and the permittivity of the space between them. The dielectrics allow us to raise the permittivity, which allows us to raise the capacitance for the same physical dimensions. But what's the purpose of the capacitor? To store energy in an electric field or a charge separation. So the higher the capacitance, the better its potential to store energy. Generally, that's a good thing. Now, how much energy is stored? You can either do this with calculus. Well, we're not going to do it with calculus. Or you can do it graphically if you understand the ideas. So if I have a parallel plate capacitor, and initially the charge on the plates is 0, then I'm going to have initially, change color. Initially no voltage and no charge. But as soon as one electron goes from one plate to the other, that's going to create a voltage. And then if I have another electron go across, the voltage is going to increase. And so if I charge the capacitor, my voltage increases linearly with the charge. And the voltage, since the definition of capacitance is Q equals VC, Q equals VC. I should have done it the other way, but that's what I have. These are the same equation, right? And so if I take this and I find the area under this will tell me how much potential energy I have stored. And so that potential energy is going to be, go away, Q over C is the height here, and this is the distance Q. So what's the equation for the area of a triangle? It's 1/2 the base times the height. So Q squared over C, 1/2. Forgot the 1/2 out front. Now that's not the equation I have written above. What's the difference? Using that equation, Q equals VC. If I replace Q is equal to CV, that's the same as let's put the square inside. So if I put the square inside, then I have one of the C's cancel, and it gives me 1/2 C times V squared. So either one of those would be an equation to tell me the correct potential energy stored. Go ahead. What is? The F is final. It's a calculus reason why I put the F there, because you can't have an integral and the limit being the same variable. So here we have a calculation for how much energy is stored by the capacitor. And you know what I didn't get to? The circuits. So we will do more circuit analysis on Friday. Have yourself a very happy Wednesday.